You write code you can read. Your processor runs numbers it never could. Between those two worlds sits a compiler, and most of the time you never see what it does in there. So let us open it up. We are going to take one tiny CX program and follow it all the way down, from the text you type to the machine code that actually runs. Every raw compiler dump you see is real output, captured straight from CX. Where I draw a diagram, I label it as a diagram. Here is the whole program. A function, count2, that takes the number n. Inside it, a loop. For I in 0 up to n, print I. And one line at the bottom that calls it with 3. 6 lines. This is everything the compiler is handed. By the end, it will be native instructions running on your CPU. Let us watch it get there. The very first thing the compiler does is read the raw text, one character at a time, and group it into tokens. The word FNC becomes a keyword. Count 2 becomes a name. The colon, the parentheses, the number 3, each one becomes its own labeled piece. It even records the exact byte range every token came from. The spaces and the line breaks are thrown away. 26 tokens in all. The program is no longer text. It is a flat list of labeled symbols. But a flat list has no shape, and code has shape. So the parser folds those tokens into a tree. The compiler's own dump is deliberately compact, a function with a single parameter, n, and a body that holds a for loop. Then, on its own, a top-level statement, a call to count 2 with the value 3. Drawn out, the nesting is the point, what sits inside what. The compiler now understands structure, not just a row of symbols. Now, the hard part. A processor has no idea what a for loop is, so the compiler lowers that tree into something far simpler. Basic blocks, straight runs of instructions joined together by jumps. This is the real intermediate representation, straight out of CX. Notice the values. V0, V1, V2. Each one is assigned exactly once and passed from block to block as an argument. It begins by setting the counter to 0, then jumps to a header block, and the header asks a single question. Is I still below n? If the answer is yes, control drops into the body, which prints I, then falls through to the increment, which adds 1, and jumps straight back up to the header. That backward jump is the loop. There is no for anywhere down here. There is a test, a body, an increment, and a jump back, repeated for as long as the test holds. And when the test finally fails, the header branches the other way, out of the loop, and the function returns. These blocks are already close to how a machine really works, which makes them easy to turn into instructions. Cranelift, CX's native code backend, takes the blocks and emits native code, real machine instructions for your processor. Then we run it. 0, 1, 2. That output was not interpreted a line at a time. It was compiled down to machine code first and then executed. But here is the question that should bother you. How do we know the compiled version is actually correct? CX keeps a second engine, a much simpler one, an interpreter that just walks the program directly, with no compilation at all. And on every single build, CX runs both of them, the compiled path and the interpreter, over the same programs, and compares the output line for line, plus the exit code. Same source, 2 completely different paths through the machine, identical result. And where the 2 cannot match yet, CX says so out loud. Some features still run only on the interpreter, and the test suite marks those honestly, instead of pretending they compile. Everything that does compile is checked against the interpreter across the suite. If it disagrees, that is a parity failure. That is the bar. Not trust me, but check it, every time. Source, to tokens, to a tree, to blocks, to machine code, and then checked against itself. One small program, all the way down. CX. Follow the build.